Hello, and welcome to Group 7's MEng project video, which will cover our high-performance non-destructive testing system for aerospace materials, which utilizes state-of-the-art quantum well eddy current field measurement technology. Safety is of paramount importance in the aviation industry due to the potentially catastrophic consequences if things go wrong, and an integral part of ensuring this safety is regular aircraft maintenance, of which non-destructive testing of aircraft components is an essential part. The non-destructive testing technique of relevance for this project is eddy current testing. Eddy current testing works by inducing a magnetic field in the material under test and then measuring that induced field. Defects and imperfections affect the magnitude of that field, and it is these changes in field that can be used to identify defects. The unique selling point of our project is the use of the quantum well Hall effect sensor to measure these values of induced magnetic field. This sensor, invented here at the University of Manchester, offers the potential to improve on the performance of existing eddy current testing techniques due to its incredible sensitivity. To utilize the outstanding performance of this sensor, we have created a fully integrated XY scanning system. The operation is simple. A sample is placed on the scanner bed and the probe head scans over the material. The key mechanical innovation is the utilization of lead screws to enable movement precise enough to detect defects as small as 0.1 millimeters. The focal point of the scanner is the sensor PCB on which the QWHE sensor is mounted. As well as the sensor, this board contains carefully chosen amplifiers which provide selectable gain of up to 1,000 at operating frequencies of up to a megahertz. The other critical component mounted on the sensor PCB is the Illuminating Electromagnetic Coil. As the probe head moves across the material, the Illuminating Electromagnetic Coil induces a secondary magnetic field in the material. It is this field that the QWHE sensor is measuring, and these values of secondary magnetic field are dependent on any defects present in the material, as the defects present in the material interrupt the flow of the eddy currents that create the magnetic field. The Illuminating Electromagnetic Coil is wrapped around a custom-made 3D printed microspool that completely encloses the QWHE sensor. This positioning ensures that the sensor is measuring the maximum possible secondary field and picking up on even the smallest of defects. The sensor and coil are then mounted on an isolating sensing PCB, which eliminates any unwanted noise, ensuring that the sensor output is as clear as possible. During the scanning process, the output of the QWHE sensor is continuously fed into a high-resolution analog-to-digital converter. Our signal processing algorithm then splits the data into the discrete blocks that will eventually make up each individual pixel of the image. The size of these blocks can be chosen depending on the image resolution desired by the user. A fast Fourier transform is then applied to each discrete block in order to extract the values of secondary magnetic field, which exist at specific frequencies in the signal, known as the sum and difference frequencies. These values are then combined to derive the intensity level of the corresponding pixel. The pixels are then finally combined in order to form a complete image of the material. Our custom image processing software then translates the output of the signal processing into an interpretable image to the user, including showing the location and size of any defects present. Operation of the scanner is completely unified by a single software solution written in Python and C. It performs the signal and image processing algorithms discussed, as well as controlling the hardware peripherals that consist of the motors, the high-resolution ADC, and the signal generator that sends the input signals to the illuminating coil and the sensor. The scanner is operated through an intuitive graphical user interface, and the software then translates the user's desired scanning parameters into the required input parameters to each of the hardware and software components. We will now show just how easy it is to use the scanning software to perform a scan. The user simply inputs their desired parameters, presses Start Scan, and the software does the rest. Multiple levels of concurrency are implemented in the software to enable the graphical user interface, the ADC, the motors, and the signal image processing code to all run simultaneously. This means that while the software is collecting the data from one row, it can perform the signal and image processing on the previous row. The image begins appearing on the screen as soon as the image processing has enough data to produce an image, which means that the user can view the output in almost real time. Our project was fundamentally successful in creating a fully integrated scanning solution that utilizes the QWHE sensor to find defects in aerospace materials. The scanner system was able to find all the defects in all the sample materials provided. Alongside this, the results were extremely reproducible, and the scanner could complete a full, accurate scan of the materials in less than 10 minutes.